What if I were to tell you that humanity's coming energy crisis could be blunted with high-efficiency wires? Or that trains could one day fly above their tracks at hundreds of miles an hour? Or probes could be sent to space with minimal cost, yet great speed? Power transmission, high-speed rails, interstellar travel, all once thought to be science fiction, are now on the horizon of innovation thanks to superconductors.
So superconductors are materials that move into a state of zero resistance at some particular temperature, which is called the transition temperature. And it's a phenomenon that was discovered in 1911 by Kamerlingh Onnes in Leiden, in the Netherlands. He was actually studying the properties of materials, which, as we all know, normally when you put current through a material, there's a voltage developed and power dissipation, like in a toaster. And he found that these particular set of materials would actually go to zero resistance. And this set off a very long study of the material. It was finally understood, I think, in 1957 at the University of Illinois by John Bardeen and his co-workers Bob Schrieffer and Leon Cooper. And they came up with a theory which really explained the zero resistance in terms of the pairing of electrons into Cooper pairs. And they were able to show that there was a ground state lower than the normal metal state.
So basically what happens is electricity comes from the motions of electrons. Ordinarily, there's a specific amount of energy that could be gained, a certain energy gap that allows the energy to be transferred. Electrons collide and then transfer energy to others, resulting in resistance. In superconductors, energy that would be gained is less than the energy gap. Therefore, electrons cannot transfer its energy. No energy is lost, no resistance, superconductivity. However, our understanding of superconductors is limited to low-temperature superconductors, ones that work at around absolute zero temperatures. What about high-temperature superconductors? How do they work?
We do understand conventional superconductors mediated by phonons. Most people believe the high-temperature superconductors are mediated by some kind of magnetic interactions. It's not completely clear how that works, and there isn't really a model. We also know that they have some very unusual properties in the normal state. Many people in this department working on what are called properties of the pseudo-gap, and most people actually believe that one of the problems with a new model for the high-temperature superconductors is that we don't understand the normal state. I think in these materials we don't really even know where the starting point is, and so that's making it a lot more complicated problem.
Even though we do not fully understand how high superconductors work, we can demonstrate how they work in a lab using liquid nitrogen to cool down high-temperature superconductors. Pouring liquid nitrogen on the ceramic disc brings it to a temperature where it begins to superconduct. When the magnet is placed above the disc, opposing magnetic fields causes the magnet to float above the superconductor. When the liquid nitrogen evaporates off and the ceramic disc comes back to room temperature, there's no longer a superconducting effect and the magnet falls to the ground. So far, superconductors have many beneficial properties: maglev trains, electricity transmission, and interstellar travel, just to name a few. What about others? What other areas of research are being undertaken?
We have a number of large projects funded by Defense Department agencies and industries to work on how to use superconductors in conventional quantum computing using qubits and also this topological quantum computing. And I think it's an area where this department is starting to focus on. It's going to be a big area for us.
Superconductivity is an ever-evolving field in modern physics. While a theory exists to explain low-temperature superconductors, high-energy superconductors still remain very much a mystery. The daunting task of exploring their secrets falls on a new generation of scientists following in the footsteps of John Bardeen, Leon Cooper, and Bob Schrieffer. Hopefully, someday soon, the field of superconductivity could deliver on its great promise of innovation and contribute to a brighter tomorrow.